What specific problem does the InfAlign framework aim to solve in the context of aligning generative language models?
The InfAlign framework aims to solve the problem of optimizing the inference time win rate of generative language models against a reference model, given a known inference time procedure. Specifically, it addresses the discrepancy between the training objective of KL regularized reinforcement learning, KLRL, and the actual inference time decoding processes, which often involve procedures like best-of-n sampling and worst-of-n jailbreaking. InfAlign proposes a family of optimization objectives that transform the reward function to align with the inference time procedure, allowing for effective training of the model to maximize its performance during inference. The framework demonstrates that by designing a suitable reward transformation, one can achieve optimal alignment for various inference time strategies, thus enhancing the model's win rate in practical applications. Ultimately, InfAlign provides a structured approach to ensure that the generative language model performs well under the specific conditions it will face during inference.
How does the proposed control method work? Please illustrate it step by step, including reward calibration, reward transformation, and the KLRL solving process.
The proposed control method operates in a three-step process to optimize inference time win rates for aligned language models. First, it begins with reward calibration, where the scores of the reward model are calibrated against responses sampled from the reference model for each prompt. This involves drawing multiple samples and assigning empirical calibrated reward scores to the responses, ensuring that the calibration reflects the true performance of the model. Next, the method applies reward transformation, where a suitable transformation function is chosen based on the inference time procedure being optimized, e.g., best of n or worst of n. This transformation modifies the calibrated rewards to better align with the specific inference time strategy, enhancing the model's performance in real-world applications. Finally, the method employs the KL regularized reinforcement learning, KLRL, solving process, where the transformed reward is used to solve the KLRL problem, typically using algorithms like proximal policy optimization, PPO. This step aims to find an aligned policy that maximizes the inference time win rate while maintaining a controlled divergence from the base policy, effectively balancing performance and safety.
Can you provide a simple example that demonstrates how the InfAlign framework optimizes inference time win rates using the best of $n sampling procedure? Walk through the main algorithm steps with this example.
The InfAlign framework optimizes inference time win rates through a structured approach, particularly using the best of n sampling procedure. For example, consider a scenario where we want to generate responses to a prompt using a language model. The process begins with the first step of the calibrate and transform reinforcement learning control algorithm, where we calibrate the scores of the reward model based on responses sampled from the reference model for each prompt. Next, we apply a suitable transformation to these calibrated scores tailored for the bond procedure, which involves selecting the response with the highest reward from n generated samples. Finally, we solve the KL regularized reinforcement learning problem using the transformed reward, optimizing the model to maximize the inference time win rate against the reference model. This three-step process ensures that the model is effectively aligned to perform well under the bond sampling strategy, leading to improved performance in real-world tasks, as demonstrated by the empirical results showing an 8 to 12% increase in bond win rates compared to uncalibrated models.
What theoretical advantages does the control method offer over traditional KLRL approaches regarding inference time win rates, particularly with best of $n and worst of $n procedures?
The control method offers significant theoretical advantages over traditional KLRL approaches by specifically addressing the discrepancies between training objectives and inference time procedures. It introduces a reward transformation tailored to the inference time win rate, allowing for optimization that directly aligns with the best of n and worst of n procedures. Theoretical findings demonstrate that the optimal solution for these inference time strategies is independent of the base policy and reward model, enabling an iterative optimization approach that can be computed offline. Furthermore, the control method employs exponential reward transformations, which have been shown to be almost optimal for BON and WAN, thus enhancing the inference time win rates significantly compared to traditional methods. Empirical results indicate that control achieves 8 to 12% higher BON win rates and 4 to 9% higher WAN win rates, showcasing its effectiveness in optimizing inference time performance.
How was the effectiveness of the proposed control method validated in the experiments, including the types of datasets used and the performance metrics compared against baseline models?
The effectiveness of the proposed control method was validated through experiments on the anthropic helpfulness and harmlessness datasets, which involved multi-turn dialogues between humans and a digital assistant. The performance metrics compared included both the standard win rate and the inference time win rates for best of n BON and worst of n WAN procedures, calculated after applying the respective inference time procedures on the responses generated by the RL model against the base supervised fine-tuned SFT model. The experiments showed that control achieved 8 to 12% higher BON win rates and 4 to 9% higher WAN win rates compared to the uncalibrated model, demonstrating significant improvements in performance. Additionally, the control method was compared against various state-of-the-art SOTA methods for optimizing standard win rate, showing that it produced better inference time win rate versus KL divergence trade-offs. The results indicated that the exponential transformation of the calibrated rewards outperformed other models, confirming the practical effectiveness of the control approach.
What limitations or challenges might arise when applying the InfAlign framework and control method to real-world scenarios?
When applying the InfAlign framework and the control method to real-world scenarios, several limitations and challenges may arise. Firstly, the empirical calibration process requires drawing a significant number of samples from the reference model for each prompt, which can be computationally expensive and impractical in real-time applications. Additionally, while the theoretical framework provides a strong foundation, the actual implementation may face difficulties in accurately approximating the calibrated reward, especially if the reward model is miscalibrated, as indicated by the observed deviations from the ideal calibration line in the experiments. Furthermore, the performance of the exponential transformations, which are designed to optimize specific quantiles of the reward, may not generalize well across diverse real-world tasks, potentially leading to suboptimal alignment outcomes. Lastly, the iterative optimization approach for finding suitable reward transformations may become inefficient or intractable when dealing with complex language models and large output spaces, complicating the practical deployment of the control method.